Hello! So we've got a parametric equations question. We've been given a couple of parametric equations here and here, and we've also been given a range for our parameter. So the parameter, remember, is the thing which we introduce. In this case, it's t, so we've got a range for that, and we've been asked to find dy by dx. So what on earth is parametric equations? Well, a parametric equation is simply taking, or parametric equations is simply taking an original function in Cartesian form. So Cartesian form is just using x and y's. So for example, I might be given x squared plus 3xy, for example, plus 4y squared equals, I don't know, 18, yeah, x over y. Yeah, let's make it really funky, okay? So we've got basically a really horrible function involving x's and y's. Now this in itself can be a bit of a headache to differentiate. I mean, sure, we know things like implicit differentiation and stuff, but sometimes that can be a bit awkward. So basically, the idea of parametric equations is that we introduce a new parameter to make this thing easier to work with. I mean, there is more to it than that. Like, you can kind of get some stuff out of looking at, by introducing, parametric equations, by parameterizing it. But I guess for you guys, the main reason why you are interested in parametric equations is because it makes it easier to differentiate and integrate things. So what you basically do is you might take sort of something that looks like that horrible function where the x's and y's are kind of all mixed in together and it can be quite difficult to look at. Okay, and what you basically do is you introduce a new parameter. So you give x in terms of this new, as a function of this new parameter. So that's basically what that is there. So it's basically saying x is just some new function involving a parameter, and you also say the same for y. So y is again some new function involving your parameter, okay, and then suddenly you can differentiate that, okay, so remember we're trying to differentiate that, so that was just an example there, okay, so I've got x equals 2 sine t, and I've got y equals cos 2t plus 2 sine t, okay, and I've been asked to differentiate that. Well, all I have to do is use the chain rule. Now remember what the chain rule is. The chain rule basically just takes dy by dx and treats it essentially like a fraction, because remember, this differentiation thing is literally like a fraction. It's like rise over run. It's basically a glorified way of finding a gradient, except it's finding a gradient of a curve, and it kind of has to take limits and things like that. Don't worry about that too much at this moment. Okay, but basically it treats dy by dx literally as a fraction. So dy is on the numerator and dx is on the denominator. Okay, well, are you happy then that if I've got dy on the numerator and dx on the denominator, I can write that as a product of two fractions, essentially. So I can have two fractions, so one here, and I multiply them together. That's what product means, okay? And whatever goes, so I have the dy on the numerator of the first fraction, and I have the dx on the denominator of the second fraction, okay? And then basically, as long as whatever goes here and here, so the numerator of the first, so the denominator of the first fraction and the numerator of the second fraction, as long as those two things are the same, then effectively they're just going to cancel off, okay? Because I'm multiplying them together, so it means that one thing with one, the numerator of one fraction cancel off with a denominator somewhere, okay? So let's say, for example, I want to just introduce, I don't know, dt. Okay, because my parameter is in terms of t, okay, so I'm going to introduce dt now. And because those two things are the same, they just cancel, and then I'm just left with dy by dx. I'm just left with dy by dx, and this is if the dt was never there, okay? So this is kind of what the chain rule is saying. It's kind of like status quo, because I've got the same thing here and the same thing here. They just cancel, and this is if the dt was never there, okay? But that's actually really useful, because look here, that's exactly what I want to find. I want to find dy by dx, and I've been given x in a function of t, which means that I can differentiate it. I can find dx by dt, okay? That's almost my second fraction. I'm going to come back to that in just a second, okay? And then I can also find dy by dt, because I've got my second parametric equation as y being a function of t, which means I can differentiate y with respect to t, okay? So I can find dy by dt, okay? And then I can just find, then finally, using this idea, dy by dx. So let's just differentiate these two things. So okay, our first equation is x equals 2 sine t. So I want to find dx by dt. In other words, I want to differentiate the x equals 2 sine t. Okay, so 2 sine t, well, the 2 doesn't actually affect the differentiation. Okay, so 2 will still stay there. So effectively what I'm asking there is, what is the derivative of sine with respect to t? So the derivative of sine is cos, so it's just going to be cos t. Hey, that was a nice easy one, wasn't it? Okay, let's try and differentiate the y then. So we've got y equals cos 2t plus 2 sine t. So basically I need to try and differentiate that with respect to t. So let's first of all differentiate cos 2t. Now, because it's cos of 2t rather than just cos of a single t, I'm going to have to kind of use the chain rule, the outer-inner rule. So I'm going to differentiate the outside first. So I'm going to differentiate cos first. So cos goes to minus sine. Okay, I'm going to actually write that like cos goes to minus sine, and I leave the inside alone, so I leave the 2t alone. Okay, and then I differentiate the inside. So what is the derivative of 2t? Well, are you happy? It's just going to be 2, okay? So the derivative of cos 2t is going to be minus sine 2t, okay? And then plus the derivative of 2 sine t. Well, if you notice, I just differentiated that up here, so it should just be plus 2 cos t. Okay, so I've got dx by dt and I've got dy by dt. Okay, what can I do with this? Well, now I come back to my chain rule. I've got all the ingredients of my chain rule. I've got dy by dx is equal to dy by dt multiplied by, hang on a minute, that's dt by dx, isn't it? That thing there is dt by dx. Well, I haven't got dt by dx, I've got dx by dt. So I want dt by dx, but I've got dx by dt. But that's okay, remember, this is just a bit like a fraction, okay? I'm just treating this at the moment like a fraction, dx by dt, differentiation, as just being a fraction. So basically, if I flip the fraction on the left-hand side, then I'm also going to have to flip the fraction on the right-hand side as well. So in other words, this thing here is currently over 1, so I just have to flip that, okay? And it just becomes 1 over 2 cos t. Does that make sense? It's just basically finding the reciprocal, okay? So dx by dt, dt by dx is just the same as 1 over dx by dt. It's just the reciprocal, or the fliprical as I call it. It just basically flips the fractions up. So if I flip the left-hand side, I also have to flip the right-hand side as well, okay? So now I've basically got, well, I have got all the ingredients I need, because dy by dt, okay, so let me just write this out. So I need dy by dx, I want dy by dx, I know that's equal to dy by dt. I know that's equal to dy by dt. Well, dy by dt is just that. So I'm going to stick that in a bracket. 2 sine 2t plus 2 cos t. Okay. Notice I'm sticking it in a bracket as well, because it makes sense to use brackets. I'm going to end up multiplying things together. It just means that things don't get lost. Like I'm making sure I'm multiplying everything I need to. So, okay, let's just have a look at this. So might as well stick it in a bracket and then multiply by, well, what do I multiply by? So dy by dx is equal to dy by dt, we've just done that, multiplied by dt by dx, well, dt by dx is going to be 1 over 2 cos t, okay? So let's have a look at this, might as well stick that in bracket. So are you happy that that basically just jumps up on the numerator? Because if I have like 3 multiplied by a quarter, okay, then that just becomes 3 over 4. So basically the number just basically jumps up on the numerator when I'm multiplying. Okay, if you're not sure about that, you can treat that as over 1, then just multiply the numerators and denominators together. Okay, so this then becomes minus 2. I'm actually going to flip it around, so I start off with the 2 cos t, because that's a positive, okay? So I'm going to start off with 2 cos t minus 2 sine 2t, and that's all over 2 cos t. So I've just multiplied that fraction together, basically. Multiply the numerators, multiply the denominators. Okay, I'm now going to separate this up into 2 separate fractions. So at the moment I've got something minus something all over 1 denominator. So I'm going to then make it into 2 fractions. Okay, so I've got 2 cos t over 2 cos t minus 2 sine 2t over 2 cos t. So all I've basically just done there is I've just basically separated the fraction up, and of course the denominator goes on the base of both fractions, okay? Because of course if you try and now subtract these 2 fractions, you'll obviously get back to here, okay? Let's have a look at this then. Well, this here is just basically 1. I've got the same numerator, I've got the same denominator, so this is just 1. Okay, so I've got 1 minus, 2 sine 2t over 2 cos 2t. 2 cos t. I'm going to look at that, because I'm looking at that, and if you remember my last video, I was looking at the implicit differentiation formula and how to do implicit differentiation. And I said to you, you need to have these double angle formulas in your head. Well, this is basically asking me, what is the double angle of sine? Okay, so I've got sine 2t, I've got sine of a double angle, so therefore I'm going to replace that with a double angle formula. And I can promise you, so I've got 2 multiplied by the double angle formula for sine, if you can remember it, okay, which you should do because I told you to write it out 30 times in my last video. Sine 2t is 2 sine t cos t. Okay, so let's have a look at this thing then. So I'm going to end up with, well, this 2 is going to cancel with this 2. Are you happy? I can then also cancel this cos t with this cos t. So what am I left with? I'm left with 1 minus just my 2 sine t, my 2 sine t in there. And that is dy by dx. And if you go back to the original question, that's what we had to find. So we've shown that dy by dx is equal to 1 minus 2 sine t. Now we've been asked to find the coordinates of the stationary point then. So remember, a stationary point occurs when the gradient is 0. So in other words, when dy by dx, that's just the gradient function, okay, is 0. So we've got dy by dx is 1 minus 2 sine t here. So we've got 1 minus 2 sine t is equal to 0. That's basically what I've done there. I've just set the gradient to be 0. It's just C1 stuff, okay? Okay, well, I guess, you know, I want to solve this equation. So let's take the 2 sine t over the other side. So I've got 2 sine t equals 1. You happy with that? And then I'll just suppose I divide through by 2. So I've got sine t equals a half, okay? So I guess, well, what is t? Well, t is just the sine inverse of a half. Now, that is a special angle, and you should know it. It's 30, so 30 degrees, but look at our range, okay? And actually, because we're using trig and calculus together, like one of the things about trig and calculus is it's much easier to work in radians when you're using trig and calculus together, okay? But also, so you should automatically give your answers in radians, basically, but also your range, or your domain in this case, is also given in radians, so you should always give your answer in radians. But basically, as a general rule of thumb, if you're using calculus or differentiation or integration, and you're using trig, okay, so you're trying to differentiate or integrate trig functions, you should always be giving your answers in radians, okay? So basically, what is 30 degrees in radians? Well, pi radians is 180, okay, so 30 degrees is 6 times smaller than that, so t must be pi by 6, okay, and if you notice our range, we're only going between basically negative 90 and positive 90, so we don't need to worry about any other angles there. So okay, have we finished? Well, no we haven't, because we found the value of t, but notice we need to find the coordinates. Well, the coordinates of our original function will be in terms of like x's and y's, like our original function will be just like x and y's just probably mixed together in some horrible function. In fact, that's the second part of the question, find that, what that original function was. But we know now that t equals pi by 6 at the stationary points. So then all we do is we stick t equals pi by 6 into our parametric equations to find out what x and y is, and then we can find out what the coordinates are. So okay, so x must be equal to 2 sine of pi by 6. Okay, so sine of pi by 6, that's the sine of 30 effectively, so that should just be a half. So it's going to be 2 times a half, which should just be 1. Okay, so then what's y? Well, y is equal to cos of 2 times t. T is just pi by 6. Okay, so 2 times pi by 6 plus 2 sine of our t, which is pi by 6. Okay, so what is cos of 2 times pi by 6? Would you happy I can do a bit of cancellation? Just make it pi by 3. Well, that's the same as 60 degrees. So what is the cos of 60 degrees? Well, the cos of 60 degrees is just a half. Are you happy? So that thing there is just going to become a half, okay, plus 2 sine pi by 6. Well, sine of pi by 6, we just established, is a half. So effectively what we've got there is 2 times a half, which just comes out as 1. So it's going to be half plus 1. So it's going to be 1.5, or 3 over 2, or however you want to leave it. So that's our two coordinates. We've got x equals 1. Okay, so our coordinates, x, y, x equals 1, and our y coordinate is 1.5. So that is the coordinate of our stationary point. That wasn't too bad, was it?